In the last lecture, we started discussing one of the very important aspects of optical communication, and that is signal distortion. We saw that the signal is distorted when it is sent on optical fiber for two reasons. One is what is called dispersion, which essentially is the pulse broadening as the pulse travels on optical fiber. Another one is the attenuation or loss of energy as the pulse propagates on the optical fiber. Then we saw that dispersion could be due to various reasons. It could be intrinsically because of the material properties, we call that as a material dispersion, or it could be because of the modal nature propagation inside the optical fiber, that we call as the intramodal dispersion. And then because of the multiple modes propagating on the optical fiber, we have what is called the intermodal dispersion. And then we saw that in a single mode optical fiber, we have material dispersion and intramodal dispersion present, whereas in a multimode fiber, all three dispersions are present, but intermodal dispersion is much higher compared to these two dispersions. The attenuation, that is the loss of energy as the pulse propagates, could be various reasons, and we will discuss this subsequently. So, in last lecture, we started discussing in detail this quantity dispersion. We defined dispersion quantitatively, and that we said if you have the relationship between omega and beta, then from there we can calculate what is called the group velocity, that is the velocity with which the pulse travels on optical fiber. Inverse of this quantity is what is called the group delay per unit length, that is this Tg. And then we said the dispersion is nothing but dTg by d lambda, that is the rate of change of group delay with respect to the wavelength. And then we got the unit for dispersion, which is picosecond per kilometer per nanometer. With this basic mathematical formulation, then we started investigating dispersions one by one, that is material dispersion, and then waveguide dispersion and intramodal dispersion. However, we said that since the dispersion is rather a weak phenomena, we quantitatively calculate the dispersion due to one phenomena at a time, assuming that the other dispersion is not present, and then the total dispersion is sum of the two dispersions. So, when we started discussing the material dispersion, we assume that the wave guiding nature or the dispersion due to the modal nature inside the fiber is not present. That means the energy is propagating as if it is propagating in an infinite medium, and then just due to because of the material properties we have the dispersion that we call as the material dispersion. So, starting with the phase constant for a unbound medium and saying that now the refractive index of the medium is a function of wavelength, we calculated the value of Tg, and from there we got this quantity what is called material dispersion, which is given by this. And then we noted here that this quantity is proportional to the second derivative of the refractive index as a function of wavelength, and then we plotted the refractive index for material glass and realized that the second derivative of refractive index with respect to wavelength gives you the curvature of the function. So, here we have a curvature of one type, here we have a curvature of opposite nature. So, curvature must be going 0 somewhere here, and that wavelength we found out to be 1.27 micrometer or 1270 nanometer. So, these are the quantitative numbers which we saw last time, that at 850 nanometer wavelength the material dispersion is rather large. It is 85 picosecond per kilometer nanometer. If you go to 1310, then you get 0.1, and if you go to 1550, you will get 20. Now we have here a positive sign and a negative sign. So if I look at the sign of this, what does the sign really mean? The dispersion is a parameter which tells you by what factor the pulse is going to broaden when it propagates on the optical fiber. So does that mean that when we have a dispersion negative, the pulse is shrinking or it is becoming more and more narrower as it propagates? The answer is no. The negative sign doesn't mean the compression of the pulse, but it rather tells you the way different frequencies are going to travel inside the pulse. Let us look at this thing in a little more detail. So let us ask, what is the dispersion which we have defined, this quantity? This quantity is dTg, that is a group delay by wavelength. So it is the rate of change of group delay as a function of wavelength. That's what gives you dispersion. So if this quantity is positive, what that means is that the slope of this time Tg as a function of lambda is positive. That means as the wavelength increases, the Tg also increases. Whereas if you have this quantity negative, the slope is negative, that means as the wavelength increases, the Tg decreases. So as I go to longer and longer wavelength, if this quantity is positive, the delay will be more and more. That means the longer wavelengths will take longer time to reach the same distance. So for positive sign, the Tg increases as lambda increases. Whereas if you have a negative sign, then you have Tg decreasing as lambda increases. What that means is that if you are having a dispersion which is positive, the longer wavelengths, since they take longer time, they are traveling with lower speed. So the group velocity essentially decreases as a function of wavelength. As the wavelength increases, the group velocity decreases. Whereas if you have a negative sign, then as the wavelength increases, the group delay decreases, that means the group velocity increases. Now you recall, when we talked about the dispersion, we said that the phenomena can be visualized as transmission of multiple signals propagating on the optical fiber. So you have this wide spectrum of your source carrier, and these are the different components which are present in the carrier. And we said the scenario of propagation can be visualized as the pulse is riding on each of these carriers and reach on the other side, and total thing what you see is again a combination of the different pulses which have traveled on different carriers. So if dispersion is positive, then we say that since now the longer wavelengths are traveling with lower speed, and longer wavelengths means smaller frequencies. So if these frequencies travel with lower speed and compared to these frequencies, then we have a dispersion which is positive. On the contrary, if these frequencies travel slower compared to these frequencies, then we have the dispersion which will be negative. Now whether these frequencies travel faster or these frequencies travel faster, the dispersion is because of the spreading of the pulse because of differential velocity between different frequencies. So if the pulse has to remain intact, all the frequencies must travel with the same speed. In one case, these frequencies travel faster, so these frequencies go ahead, these are left behind. In the opposite sign for dispersion, these frequencies travel faster, these frequencies are left behind. In either of the case, there is going to be a pulse broadening. There is no shrinking of the pulse. So, if I look at internally the pulse, if the dispersion is positive, then the longer wavelength would be left behind within the pulse and shorter wavelength would go ahead. So, in this case, if I look at my pulse spectrum and ask internally how the frequencies are going to look like. So, this is my pulse which is transmitting. Originally all the frequencies were together at every point in this pulse. Now, we will see that there is an accumulation of the longer wavelengths. Since it is taking more time, they will be getting accumulated on this end. So, you have here lambda, longer wavelength, and here you will get a lambda which will be shorter wavelength. So, the frequency separation is going to take place inside the pulse because of this dispersion, and for positive dispersion the shorter wavelength will go ahead and the longer wavelength will be trailing behind. If you take a negative dispersion, then exactly opposite would happen. Again, as far as the envelope is concerned, it will be exactly identical to this. So, you will again get a pulse broadening exactly by the same amount. Only thing is now lambda longer will come here and lambda shorter will go here. So, the sign of dispersion essentially changes the distribution of frequencies of the carrier inside the pulse. But if you look at the envelope as a whole, the envelope is affected exactly in the same way whether dispersion is positive or negative. So, in one case the plane is shifted like this, in the other case the plane is shifted like this. But if you look at the projection in time, it will give you exactly the same kind of broadening. What that means is that the pulse broadening is actually given by the modulus of this quantity d. So, though we define this quantity dispersion as dTg by d lambda, as far as the pulse broadening is concerned, that is given by modulus of this quantity d. So, until and unless one is interested in finding out how the frequencies are separated inside the pulse, the sign of the dispersion does not matter. Whether dispersion is positive or dispersion is negative, as long as the magnitude of the dispersion is same, it gives you the same broadening irrespective of the sign of the dispersion. So, this is the material dispersion now. The next dispersion which we want to investigate is what is called the waveguide dispersion. And as I mentioned earlier, when we now discuss the waveguide dispersion, that means this is a dispersion due to the modal nature inside the optical fiber. We have seen this diagram, the BV diagram, where V is the V number of optical fiber and that is proportional to the frequency. We have this quantity B which is normalized propagation constant, which is related to the phase constant of a mode. So, from this diagram we would like to find out what would be the group velocity and how it would vary as a function of wavelength. We also recall that the BV diagram is not a linear diagram. So, BV relationship is not linear, there is a non-linear function there. So, as a result we expect that there would be some kind of a pulse broadening because of this wave guiding nature. So, as we mentioned earlier, we take one dispersion at a time. So, now when we investigate the waveguide dispersion, we assume that the material dispersion is 0. That means the core and cladding material do not have intrinsically any dispersion. Only dispersion which is going to be there is because of the guided nature of optical fiber. So essentially we would like to find out this parameter dispersion in terms of the parameter which are B and V. So let us do a small derivation to get a relationship between the dispersion and the parameters B and V. So you recall we had defined the quantity B, which is equal to beta square minus beta 2 square divided by beta 1 square minus beta 2 square, where beta 1 and beta 2 are the phase constants intrinsically in medium, core and cladding, and beta is the propagation constant of that particular mode. Now recall that we also have in practice the optical fibers for which the refractive index N1 and N2 are very close to each other. That means for a practical fiber, what we call as the weakly guiding fiber, we have seen that N1 is approximately equal to N2, because the difference between them is typically of the order of about 10 to the power minus 3. You also recall that we had defined a parameter delta that is equal to N1 minus N2 divided by N1. And since N1 is approximately equal to N2, I say approximately this quantity is also N1 minus N2 divided by N2. We have also seen that when a mode propagates, the phase constant of a mode is bounded by beta 1 and beta 2. So beta lies between beta 2 and beta 1, which is nothing but N2 into beta 0, and this is N1 into beta 0. Since N1 and N2 are very close to each other, the range over which this beta changes is extremely small. So what that means is that this quantity, the difference quantity which we have, beta 1 and beta 2 they are almost equal. So if I can factorize these two, we can write this as beta minus beta 2, and this is beta plus beta 2 divided by beta 1 minus beta 2 and beta 1 plus beta 2. Now since this beta 1 and beta 2 are very close to each other, this beta plus beta 2 is almost equal to beta 1 plus beta 2. So we can say that this is approximately equal, so this can cancel. So we can linearize this relation as this is beta minus beta 2 divided by beta 1 minus beta 2. So to do a simple calculation for the what is called the waveguide dispersion, first we linearize this quantity B under the assumption that the fibers are weakly guiding fibers. That means the refractive indices of core and cladding are almost same. The difference between them is very, very, very small. Once you do that, then I can invert this relation and find out this quantity beta, which I can do as beta that is equal to beta 2 plus B into beta 1 minus beta 2. So I just take this beta 1 minus beta 2 here, bring beta 2 on the other side. So you get this now phase constant beta for mode, which is given by beta 2 plus this quantity. Now I can take this beta 2 common from here. So you get beta 2 1 plus beta 1 minus beta 2 upon beta 2. Now this quantity beta 1 is n1 into beta 0, this is n2 into beta 0, and this will be n2 into beta 0. So beta 0 will cancel. So this quantity will be n1 minus n2 upon n2. So you can write here, this is beta 2, which is 1 plus b n1 minus n2 upon n2. And this quantity is nothing but the fiber parameter, what is called delta. So we can write this expression now in terms of beta 2, 1 plus b into delta. So after linearizing, we get the phase constant of a particular mode, which would be essentially given by this. And now I can write down this quantity beta 2 explicitly in terms of frequency and the refractive index. So this could be omega by c into n2. So it is beta 0 into n2, where omega is the frequency, multiplied by 1 plus b into delta. Now note here this quantity b, which is the normalized phase constant or propagation constant, that is a function of omega, or that is a function of lambda. So now to find out dispersion, as we have done in our basic formulation, first we find out what is called the group delay, which is d beta by d omega. So we have group delay Tg, that is equal to d beta by d omega. So if I differentiate this with omega, we get this is equal to n2 by c 1 plus b delta plus n2 omega by c dB by d omega. We want to finally derive the expression in terms of BV diagram. So what we want to do is, we want to change this derivative dB by d omega in terms of the derivative with respect to the V number. Because once you have a BV diagram, we can find out the slope or the curvature of the BV diagram. So essentially we can find out the derivatives of B with respect to the frequency omega. So what we can do is, we can write this expression a little differently. So we can get here Tg, which is equal to n2 by c 1 plus b delta plus n2 omega by c. This one we can write down as dB by dV into dV by d omega. So the derivative which we have here dB by d omega, we can write here as a dB by dV into dV by d omega. Now recall, we have this number V number, which is defined as omega by c into A into the numerical aperture. So if I calculate this quantity here, dV by d omega, that is nothing but A into numerical aperture divided by c. So that is equal to, if I can multiply this by omega divided by omega, if I multiply by omega, the whole quantity will become V. So this is nothing but V upon omega. So I can substitute into this to get the group delay, that will be equal to N2 by C 1 plus B delta plus N2 omega upon C dB by dV into dV by d omega, which is nothing but V upon omega. So I have V upon omega. This omega cancels with this. So you will get a quantity here N2 upon C, which will be common with this. So you can rewrite this N2 upon C into 1 plus B delta plus V dP by dV. There has to be delta here. You got quantity here delta. Here delta. Now taking this delta common from here, you can combine these two to write more compactly. This is N2 by C into 1 plus delta dBV by dV. Note here, if I expand this, it will be B times dV by dV, which is 1. So that gives you delta into B. The second term will be B into or V into dB by dV, which will be this term. So now the group delay in terms of the BV diagram parameters is essentially given by this. Now note here this quantity N2 by C, if I see, this is nothing but the group delay which the signal will undergo if it was travelling in the medium cladding of a refractive index N2. So this parameter is a constant delay which signal will undergo anyway. This is the quantity essentially which is telling you the differential velocities. So this is the term which essentially will give you something which we are interested in, that is the dispersion. So every signal is going to undergo a delay which will be this thing which is constant, which is not a function of wavelength or frequency. This is the term which is going to give you differential delay, and that's what will give you dispersion. So now having got now this quantity here Tg, then the next step is the dispersion, which is Tg by T lambda. So we can get now the waveguide dispersion. Let us call it dWg. That will be equal to dTg by d lambda. So I can take this quantity dTg and differentiate with respect to lambda. Firstly, this quantity is constant, so that derivative is 0. So what I get is equal to N2 delta by C d by d lambda of dBV by dV. Again, we can do the same thing as we did in the previous case. This I can write as d by dV multiplied by dV upon d lambda. So you can write here this is N2 delta upon C. So if I write this d by dV, this will become d2 bV by dV square. So I have here d2 bV by dV square into dV by d lambda. Again, writing the V number now in terms of wavelength rather than in terms of omega, we know that V omega by C A into numerical aperture, that is the V number. But omega we can write as 2 pi f, and C upon f will give you wavelength. So this also can be written as 2 pi by lambda into A into numerical aperture. So dV by d lambda will be equal to minus 2 pi A into numerical aperture upon lambda square. If we give one lambda here and one separate out, 2 pi A numerical aperture upon lambda will be nothing but again the V number. So this quantity can be written as minus V divided by lambda. So we can substitute now this quantity into this. We get what is called the waveguide dispersion in terms of this BV diagram parameters. So we get dWg, that will be equal to minus N2 delta upon C V upon lambda d2 bv upon dv square. So once we have the BV diagram known, then from there we can calculate this quantity B into V, and then we can calculate second derivative of this quantity, and from there we can essentially calculate the waveguide dispersion. Of course, since the BV diagram doesn't have any analytical form, this derivative has to be obtained numerically. So firstly, you should have a very accurate value of B measured or calculated as a function of V number, and from there then you can calculate what is called the waveguide dispersion. Now again, looking into this expression, one doesn't get a feel what should be the V number for operation, so that I get this waveguide dispersion as small as possible. So again, one has to go numerically to find out from the BV diagram. So if I now consider the BV diagram and from there I find out this waveguide dispersion, we find that for the LP01 mode or HE11 mode, that is the first mode which can propagate, the waveguide dispersion peaks around V number of 1.2. So if I go on either side of V number 1.2, the dispersion reduces. So that means if we want to have waveguide dispersion, then either I have to operate at a V number much smaller than 1.2 or at a V number which is much larger than V.1.2. Obviously, if I go to a V number which is much less than 1.2, then since the V number is very small, either the numerical aperture has to be very small or the radius of the fiber has to be very small. So that is not a very good option, because both of these essentially are going to affect the launching efficiency of the optical fiber. So ideally we should operate at a V number as large as possible, as we have seen earlier, and now we are saying that we should operate at a V number which is much larger compared to 1.2. So now we have restricted the operation range for V number still further, that we cannot go to a V number more than 2.4, because if the V number is increases more than 2.4, the fiber does not remain single mode. So for single mode operation, V number has to be less than or equal to 2.4. But now the V number has to be more than 1.2. So what we find is, to reduce the waveguide dispersion, essentially we should go as close to again the V number 2.4, so that the waveguide dispersion is small. Of course, it has not become very small. It is about 20% of what you would get around the peak, around the V number which is 1.2. So you cannot make the waveguide dispersion very small because you cannot operate the fiber at a V number which is greater than 2.4. So that's why, as I mentioned earlier also, to guarantee the fiber to be single mode and to reduce the dispersion on the optical fiber, the V number has to be very close to 2.4 but less than that. So now if I consider a single mode optical fiber, we have both this dispersion present. One is the material dispersion and other one is the waveguide dispersion. And total dispersion is approximately equal to sum of these two dispersions. Now since both these dispersions are because of the finite bandwidth of the signal, these dispersion together we call as the chromatic dispersion on the optical fiber. So we have quantity what is called chromatic dispersion, and this is approximately equal to the material dispersion plus the waveguide dispersion. So we have calculated now the material dispersion from the properties of the glass. We have calculated now the waveguide dispersion, and if we combine these two, we will get the net dispersion on the optical fiber. Note however is that the material dispersion is a property of glass, so it is completely out of your control. Once you identify the material glass, this d material is decided. This quantity here, however, d waveguide, that depends upon the BV diagram, and BV diagram depends upon the V number, which depends upon the size of the fiber, the refractive index difference, numerical aperture, and so on. So this is the quantity which is a structure dependent quantity. So if I change either the refractive index of the fiber or size of the fiber, this quantity is going to change. So d waveguide is a fiber based parameter which can be controlled, and later on we will see, we will try to make use of this fact that the waveguide dispersion can be manipulated, and as a result the total dispersion on the fiber can be manipulated. But at the moment it is enough to note that the material dispersion is almost like God given, but the waveguide dispersion can be manipulated by changing the fiber parameters. So now if I take the total dispersion, then as we mentioned, it is sum of the two. So here this green line gives you the material dispersion. The blue line here is the waveguide dispersion for He11 mode in a single mode fiber. So the total dispersion will be sum of these two. So if I take these two curves and add them point by point, I will get this red line. That is the total dispersion I will see on the single mode optical fiber. Recall, when we talk about the material dispersion, we have seen that the material dispersion goes to 0 at a wavelength which is 1270 nanometer. However, when I make a single mode optical fiber, I do not see this 0 dispersion point at 1270 nanometer, because we always see a combination of the waveguide dispersion and the material dispersion. So effectively we will see this point where the dispersion would go to 0, and that point is 1310 nanometer. So inside a single mode optical fiber, the 0 dispersion point is not 1270 nanometer as it is for the intrinsic material, but it is around 1310 nanometer. That means if I can take a single mode optical fiber and illuminate this with a wavelength which is 1310 nanometer. Dispersion on this wavelength is almost zero. That means it can really support a very large bandwidth or very high data rate at 1310 nanometer. If I go to a wavelength which is 1500 nanometer or 1550 nanometer, again the dispersion is large. So, pulse broadening is large, and as a result the data rate is reduced. So, if you see from data rate point of view, 1310 nanometer is the best wavelength in a single mode of fiber, because that is the wavelength at which the dispersion is almost zero. Why I am using the word almost? Because as soon as you try to put a finite band of wavelengths, we do not operate at a point where this curve is zero. We will be having a very narrow region around it. So, one point of this curve is zero, but in that small wavelength range, every point will not have a zero dispersion. So, you will see some dispersion, but that dispersion will be extremely small compared to what you get at a point here which is 1500 nanometer, or you take a point here which will be about 800 nanometer. That is the reason 1310 nanometer was immediately chosen window after the first generation, because at that wavelength one could see a scope of sending extremely high data rates on the optical fiber. So, 1310 nanometer, that's why is a special window, because it can support the highest possible data rate. Now, the total dispersion which we are seeing here, since it is a combination of these two, the material dispersion and the waveguide dispersion, this curve is fixed as I mentioned, but this curve can be changed. Either it can be changed like this, or it can be shifted up or down, and as a result the total dispersion on the fiber can be manipulated. We will come to this aspect little later, that by changing the waveguide dispersion, what way the total dispersion characteristics can be modified, and what way we can get much more broadband systems by manipulating the waveguides on the single mode optical fiber. Let us now turn our attention to the second important parameter which causes distortion on the fiber, and that was the attenuation. So, we saw for the attenuation we have various mechanisms. The signal on the fiber can be attenuated due to intrinsic material properties. So, like any other material, you have absorption of energy as it propagates. So, intrinsically you may have a loss because of absorption. But more stronger loss which you see inside the optical fiber is what is called the scattering loss. Now, what is the scattering loss? When I considered the optical fiber initially, we said that the refractive index of core is N1 and refractive index of core is N2, and there is absolutely constant inside the core and cladding. However, when I manufacture an optical fiber, you will see that there are very small micro centers which are developed, which have a refractive index little different than the average value. In other words, we have some kind of regions which are created inside the optical fiber, which are distributed all through its length, and these sizes are very, very small, fraction of a micron. So, when the light tries to propagate through this, it sees a small perturbation in the refractive index. This phenomena is very similar to when the microwave signal tries to propagate in the atmosphere, and if there are raindrops, that microwave signal gets scattered by the raindrops. Precisely the same phenomena which you see here, that these microcenters have sizes smaller than the wavelength. So you see scattering of light taking place because of this, and that scattering is what is called the Rayleigh scattering. So essentially, due to this, a very tiny fraction of light gets scattered into all directions, at everywhere. Now recall that for a sustained guiding of light, the light must be confined within the numerical aperture cone. So let us say if the numerical aperture cone was this, any light which is scattered outside this numerical aperture cone will not get guided and will be lost from the sides of the fiber. That's what is called the scattering loss. And the Rayleigh scattering is a very strong function of the wavelength. The Rayleigh scattering goes as lambda to the power minus 4. That means for every doubling of wavelength, the Rayleigh scattering loss would reduce by a factor of 16. It is lambda to the power minus 4. So if wavelength is doubled, it is 2 to the power minus 4. So you will get a reduction in the loss by 2 to the power 4, which is 16. Primarily, that is the reason why the fiber shows low loss at 1500 nanometer compared to 800 nanometer. Because from 800 nanometer to 1550 nanometer, the wavelength ratio is approximately 2. So you see a substantial reduction in the loss because of the Rayleigh scattering. So if I take this and plot this loss as a function of wavelength, the Rayleigh scattering loss will go at lambda to the power minus 4, which essentially is given by this red line. So what we are showing here you is a plot as a function of wavelength, where wavelength is going from 0.5 micron to almost 10 micron here, and that is the Rayleigh scattering loss. So as you can see, this drops very rapidly as the wavelength increases. However, as we know that for glass there is another loss, what is called an infrared loss. The glass is a very bad conductor for infrared. So all infrared get very rapidly attenuated when they propagate inside the glass. So as you go to longer and longer wavelength, the loss increases very rapidly. So the blue line here essentially shows you a loss which is because of the infrared absorption inside the glass. So now we see something interesting. As we increase the wavelength, the scattering loss decreases. But as you go to very long wavelength, much deeper in infrared, then the infrared loss starts dominating, and again the loss starts increasing. So the total loss profile, if you see, it is like a valley here which is created. The loss has decreased because of the scattering and started increase again because of the infrared absorption. There is also an impurity, what is called the OH molecules, which normally remain inside the glass. These are the water molecules. So even if you purify glass to a very high accuracy, when the glass is exposed to the environment, typically the water molecules slowly get diffused inside the glass, or even in processing time, you cannot really remove completely the water molecules. And water molecule gives you the absorption peaks at various wavelengths, and one of the peak lies exactly on this valley where the loss here is minimum. So this peak which you see here, that is because of the OH absorption. Of course, now the technology has improved and people have removed this OH absorption loss. So now we practically have a window which is just corresponding to this value. But because of this OH absorption loss, essentially this low loss window which is created by this valley has been split into two. And that's what precisely we find in the overall loss profile of the glass, as you have seen in the earlier lecture. So this portion here has been enlarged. So if I consider a region around this, and if I enlarge this, we get a loss profile which looks like this. So this is that OH absorption peak. This is one of the windows. This is another window. And this window is 1310 and this window is 1550. So now it makes sense why this 1310 and 1550 windows were chosen. Primarily they come because of the dispersion considerations and because of the loss consideration. Of course, this loss which you are talking about is intrinsically because of the fiber characteristics. That means as soon as the fiber is made, you will always have a loss which is the absorption and which will be scattering. But in addition to that, when the fiber is laid into the system, then the fiber has further loss incurred, and that is because of the environmental or deformations of the fiber. So either fiber can be deformed at a very small spatial scale, or it can be defined at a very large spatial scale. And both of these essentially contribute to the loss. So the scattering loss and the absorption loss are present inside the optical fiber even in the ideal conditions. That means even before laying the fiber in system. If I lay a fiber, however, in the system, and because of all the mechanical pressures, the fiber get deformed at a micro scale. So ideally the fiber core and cladding should have remain absolutely straight, but because of these pressures, you can have a micro deformations on the core and cladding of the optical fiber. Now these pressures are extremely tiny. For example, even if you touch the fiber, that kind of pressure is good enough to create this kind of deformations. Now note here, if the fiber was absolutely straight, these boundaries are straight like this, ray will get propagated by total internal reflection. But if the fiber is deformed like this, then essentially what is happening is locally now the normal is changed. This is the normal now. So the ray which was satisfying the critical angle condition when the normal was like this, no more satisfies the critical angle condition. And as a result, that energy essentially leaks out, something like this. So what we find now is that when the fiber has what are called the micro bendings, then there is a small amount of energy which leaks out from the fiber. And this is what is called the micro bending loss inside the optical fiber. So when the fiber is laid, is commissioned into the system, in addition to the intrinsic loss which is scattering and absorption, you will also have the micro bending loss present inside the optical fiber. There is one more loss which is there, which is if the fiber is bent gently, and that loss essentially we will investigate when we meet next time. That is what is called the radiation loss. And then we will see as a whole the attenuation and dispersion characteristics of the fiber to get some conclusions about the signal distortions on the optical fiber.